A closed loop is held stationary in a magnetic field between the north and south poles of two permanent magnets held fixed. Can we hope to generate current in the loop by using very strong magnets? Okay, first we'll try to understand the question. Loop is held stationary in a magnetic field. Then two permanent magnetic are held. Here loop is also stationary and magnet is also stationary. Please note the point. Loop is stationary, magnet is held fixed, magnet is also stationary. According to Faraday's law, whenever there is a change in the magnetic flux, EMF is produced. When loop also stationary, magnet also stationary, the produced flux also constant. There is no change. So, answer is no, current cannot be generated even with very strong magnetic field because there is no change in the flux. Okay, we'll go for the second part now. A closed loop moves normal to the constant electric field between the plates of a large capacitor is a current induced in the loop. When it is wholly inside the region between the capacitor plates, when it is partially outside the plates of the capacitor, the electric field is normal to the plane of the loop. Yes, here also answer is no because to produce induced EMF, there should be a change in the magnetic flux, not electric flux. According to this question, electric field is there in between the loop, right? Capacitor means electric field. Electric field alone does not produce induced current. Induction requires changing magnetic flux, not electric flux. So, in case B also, it is not possible. We'll go for case C now. A rectangular loop and a circular loop. Rectangular loop and a circular loop are moving out of a uniform magnetic field. Yes, uniform magnetic field, both are going out. Magnetic field region to the field free region with a constant velocity. In which loop do you expect the induced EM to be constant during the passage out of the field region? The field is normal to the loop. Yes. So field is normal, into indicates normal. Both are going out. How they are going out? They are going out with a constant velocity. Now, what we have to find out? Okay, both are going out when it is partial. The field is normal to the plane. Okay, we'll see now. Induced EMF, first we'll check. What is induced EMF? d phi by dt, B into dA by dt. Induced EMF depends upon two factors, right? Magnetic field as well as rate of change of area. In this case, constant magnetic field. So I have taken B outside now. There will be change in the area. Yes, when the loop is moving in this direction, the area continuously, area in contact with the field continuously decreases. There will be change in dB by dt. Now, when a rectangular loop moves, what is the area of the rectangular formula? Length into breadth. Constant length and breadth goes out. In other words, dA by dt remains constant. See the shape here. Okay, this much length has gone, this much breadth. So, matlab, area of the portion which is going out remains constant. With respect to time, dA by dt constant. But in the case of circle is not symmetric shape. So, this part, first little area, then little more area, then again little more area. So, it is not constant. dA by dt continuously changes. So, our answer is rectangular loop has constant induced EMF. Now one more part is there, right? Okay. Uniform area changes matlab constant EMF. Non-uniform area changes means there will be a varying EMF. We'll go for the last part. It's a very interesting question. Predict the polarity of capacitor in the situation described by figure 6.9. There is a coil vertically kept and a capacitor is introduced here. We have to find the polarity. This is North Pole, this is South Pole. What we know, when North Pole is coming toward the side of the coil which is near to North behaves like North. There is a great opposition. Similarly, when south pole is coming, this side will behave like south and other side will behave like north. This much we understood. Okay. Now we have to identify the polarity of A and B. Left side, this side is north and this side is south. Direction of field lines from north to south. I will draw the field lines here. North to south. Now I'll use my right hand thumb rule. What type of field lines here? Is it clockwise or anti-clockwise? It is anti-clockwise. Now take the direction in anti-clockwise. Curled finger gives the direction of magnetic field lines. Keep your thumb such that the curled fingers are along this direction. Where is your thumb? Upward or downward? Yes, thumb is going upward. Means current is flowing upward. Now current is going upward. Current is flowing like this. Flowing upward. Current always starts from positive terminal. Suppose if you construct a battery here. Current generated, it is continuously flowing. Now let us draw the battery here. Current flows from positive and comes to negative. Positive means this should be positive terminal. Down will be negative terminal. Battery in between the show. The direction of current A is connected to positive, plate A positive and plate B negative. First step, you are marking which side is north, which side is south. Then magnetic field lines. Then right hand thumb rule, you are finding the direction of current. So current always from positive terminal. So this is positive. It is connected to positive. That is our imagination, right? This is positive and down is negative.